Welcome to the Struct Soft Center community.
Hello everyone, welcome back you all in this new video. In this video, we are going to discuss about professional approach for the manual design of rectangular footing with axial load and biaxial movements. This complete problem we are going to solve in a few important steps. In the first step, we will discuss about the problem statement, preliminary size of the footing and trial depth of the footing. In the second step, there will be design for the flexural reinforcement along the length and width of the footing. In the third step, we will do the design checks for one-way shear and two-way shear. In the fourth step, we will do the stability checks for uplift, sliding and overturning. And finally, in the last of this video, I will give you some bonus tips and tools to do the complete design by a smart tool. If you are going to do this complete design manually, that will take 1 to 2 hours. But in the last of this video, I will show you one important tool. By using that tool, you can do this complete design in just of 2 to 3 minutes. So I would like to request, please watch this video till its end for better understanding of everything. First of all, let's try to understand the problem statement. A column 230 by 600 in mm is transferring a load of 1350 kN as axial load and biaxial moment as 15 kN about the major axis and 20 kN about the minor axis. So if you are going to see the figure here, so the major axis is the axis which is passing through the width of the column and width of the footing, and about this axis the moment is given as 15 kN, and about the minor axis means the axis which is passing through the length of the footing, or we can say along the depth of the column. So this movement is actually 20 kN. This is the minor axis, this is your major axis. So we have given both movements, and this column is also carrying the axial load of 1350 kN. We have to design the foundation by considering the grade of concrete as M30 and grade of steel as Fe500. The SPC of the soil is given as 375 kN per meter square, and the permissible settlement for this foundation is 25 mm. So in the first step, we are going to find out the preliminary sizes of the footing. So we have given the data as the axial force 1350 kN, moment about the major axis as 15 kN and moment about the minor axis as 20 kN. So first of all, we have to calculate what total load is going to be transferred to your soil through your column. So one load is carried by your column, that is nothing but 1350, plus we have to add the self weight of the footing, and by considering the self weight of the footing, we are going to consider the 10% of the axial load. So it is going to become 135 kN. So pure axial load coming through your column plus self weight of the footing combinedly will give you the final load which is actually going to be transferred to your soil through your footing is going to become 1485 kN. This is the total axial load which is going to be transferred. Now we have to calculate what area of the footing required. So area of footing required will equal to total intensity of the load, axial load 1485 divided by 375. If you are going to take this, you will get the value of area requirement as 3.96 meter square. Here important note is that footing length and width should be fixed to maintain the uniform pressure distribution, and this is possible only when you are succeeded to provide the equal projection from all sides of the column. What does it mean? Try to understand, it is very important. Whenever we are going to design the foundation, so we are expecting that the pressure distribution throughout the area of the footing, entire area of the footing, along length, along width, everywhere, the upward soil pressure should be what? Uniform. It should not be non-uniform. this is what our trial. So if suppose you want to get a uniform pressure distribution at the base of the footing, what step you need to take? You should try to take a same projection on all sides of your column till its edge of the footing. So this should be equal. If you succeeded to maintain it, then we can ensure that the upward soil pressure will be uniform and design will be economical and the reinforcement demand will be uniform. So everything will be what? Uniform only when you will be succeeded to maintain the same projection from all of the sides of your column till the edge of the footing. So for that reason, what we are going to do here, width of the footing, length of the footing, if you are going to multiply this, you will get the area of the footing. So area of the footing we have already calculated 3.96 meter square, but we don't know separately what is the length of the footing, what is the width of the footing. So here width of the footing will equal to width of your column plus 2 times x. This is the width of your column, and this x and this x is going to become 2x. So we will get total width of the footing. Likewise, we will get the total length of the footing. How we can calculate it? This is the depth of the column. We are going to denote it by A. So here it is what? A plus this x and this x, it is going to become 2x. So A plus 2x. So we will get a total length of the footing, total width of the footing. Okay. Now here finally these two values we are going to put in this. If you are going to put it here, so what is going to become? B plus 2x into A plus 2x will require to provide 3.96 meter square area of the footing. Here we are knowing what? Width of the column 230 mm, depth of the column as 600 mm. Now put these two values in this formula, but the values should be what? In meter. So 0.23 plus 2 times x multiplied by 0.6 plus 2 times x will equal to again 3.96. If you are going to solve this equation, you will get one quadratic equation as 4x square plus 1.66x minus 3.822 as equal to 0. On solving of this quadratic equation, you will get acceptable value of x will be as 0.792 meter. This value you will get if you are going to solve this quadratic equation. Definitely you will get two values. So acceptable value will be this one. Now I am going to put this x value in width of the footing formula and length of the footing formula. So after putting all of these values in this width of the footing formula, we are getting the value of width of the footing required as 1.814 meter. I am going to round up this value to 1.9 meter. Likewise, there is a formula for the length of the footing, A plus 2 times the x value. So A is 0.6 plus 2 times 0.792. So length of the footing required here as 2.184 meter, and we are going to round up this value to 2.2 meter. So finally we are getting the value of width of the footing 1.9 meter, length of the footing as 2.2 meter. These two values we are having now. So we have finally finalized the length and width of the footing, but I would like to mention that this length and width of the footing has been decided without of considering the influence of the movement. If you are able to recall, so we have not considered movement about minor axis, movement about major axis. These two movements we have not considered. This length and width of the footing we have calculated only on the basis of your axial load. There is no any consideration of the movement, but we have to take the consideration of movement for the calculation of the length and the width of the footing, because your footing is not going to be subjected to only the axial load. Your footing is going to be subjected to movement as well, including of your axial load. So how your movement is going to influence the design of the footing and especially the sizing of the footing, we will discuss it in detail. Now we are going to introduce the movement into the calculation. So here important given values and the formula. Total axial load including the self weight of the footing is 1485 kilonewton. We already have done the calculation for this. If I would like to show you here, it is the total P value, that is 1485 kilonewton. So here it is written. Now movement about the major axis 15 kilonewton meter, movement about the minor axis 20 kilonewton meter. Keep in your mind. Area of the footing provided. What is the area of the footing provided? That will be equal to width of the footing and length of the footing. If you are going to take the multiplication of these two things, you will get the area of the footing. And third formula is about the sectional modulus. What does mean the sectional modulus? So it is very simple. So the basic formula for the sectional modulus is what? Sectional modulus about a particular axis, let's say major axis. So that will equal to moment of inertia about that particular axis, about the centroid about that particular axis. So moment of inertia about xx means about the major axis moment of inertia. So it is passing through the width of the footing. So moment of inertia xx will equal to what it will be? Width multiplied by length cube divided by 12. Okay, as axis passing through the width, so that's why it is width multiplied by this length cube divided by 12, and yxx will equal to half of this length. Okay, so this length divided by 2 center. If you are going to put these two value here, what you will get? BL square by 6. This value you will get as a sectional modulus about major axis. Likewise, you can do the calculation for the sectional modulus about the minor axis. So both the formula are actually given here. If you are going to say sectional modulus about the major axis, BL square divided by 6, and sectional modulus about the minor axis, LB square divided by 6. Now when you are going to do the design for the normal footing, when it is subjected to only the axial load without of the movement, at that time how we will calculate the pressure? Upward soil pressure we are calculating by the formula of upward soil pressure will be equal to total axial load divided by area of the footing provided. This will give you pressure value. But in our proposed problem, there is not only the axial load, there is a presence of the movement as well. So that's why the maximum pressure will also include the addition of the pressure due to your movement about the major axis, pressure due to movement about the minor axis. So you have to add all these values to get the final maximum pressure. And likewise we have to subtract these two values from the base pressure, so we will get the minimum pressure. So this will be your final upward soil pressure as maximum, final upward soil pressure as minimum. These two things we need to calculate. So we are going to proceed for calculating all these values with our first trial. So we already have decided the length and width of the footing. So 1.9 and 2.2 meter length and width of the footing actually safe only for the axial load, but we are going to include the movement also. Now we have to check whether this width of the footing, whether this length of the footing is safe or not when we are going to consider the movement as well. So the formula is what? Area of the footing. What is? Width and length. Width multiplied by length. If you are going to multiply 1.9 with 2.2, you will get the area of the footing as 4.18. Sectional modulus about the major axis. The formula here is given. So B, put here as B, and here length 2.2 square divide by 6, you will get the sectional modulus about the major axis, and likewise you will get the sectional modulus about the minor axis, and finally base pressure P by AP, we are going to get the value of 355.26. we are having all the values. We are having the total P value, we are having total AP value. So if you are going to take this 2 ratio, you will get the value of 355.26. Now moment about major axis divided by sectional modulus about the major axis. So we are getting 9.79. Moment about the minor axis divided by sectional modulus about the minor axis, we will get the value of 15.11. Now guys, important thing is that to calculate the maximum pressure and minimum pressure. How you can calculate the maximum pressure and minimum pressure? Try to understand. P by AP, this value plus this value plus this value, you will get the maximum pressure. We are getting it as 380.17. Now next, minimum pressure. Minimum pressure, how you can calculate? This total value minus this value minus this value, you will get the minimum pressure. Next, we have to check whether this size of the footing is safe or unsafe. How you will come to know about this? You have to check maximum pressure. If this maximum pressure is less than of your SBC of the soil, then you can say it is safe. So our SBC of the soil is given as 375 kilonewton per meter square, and we are getting the pressure as about 380.17. so it is not okay, it is failing. Your upward soil pressure maximum should not be more than of the SBC of the soil. And another check will be what? Minimum pressure. So your minimum pressure in any of the case should not be less than of 0. So here our value of the minimum pressure is not less than of 0. So in respect of this criteria it is okay, but in respect of maximum pressure criteria it is not acceptable. So both criteria should be satisfied at the same time. If any one criteria is suppose not going to be satisfied, that size of the footing will not be acceptable. So that thing here given in the note, that is what? In the first trial, the calculated maximum pressure 380.17 is more than the safe bearing capacity of the soil 375 kilonewton per meter square. Hence it is unsafe and the size of the footing is not acceptable. That's why it is failing. Then what to do? Take a next trial. We are going to take another trial. So what we will do in the next trial, we are going to increase the width of the footing as well as length of the footing by 0.1 meter, or you can say 100 mm. So 1.9 we are going to change it to what? 2 meter, and length of the footing instead of 2.2 we are going to take it as 2.3 meter. So in an equal proportion we are trying to increase it, because remember what we have considered, we have to maintain the equal projection from the column up to the edge of the footing in all the direction as much as possible. It will not always be possible to get the same value, but you should try to keep it same as much as possible. Okay, so 2 and 2.3 meter we are going to take. Repeat the same calculation again and you will get all this value. Total area of the footing 4.6. If you are going to multiply this 2 value, 2 into 2.3, you will get 4.6. Sectional modulus, these values about the major and minor axis. Pressure, total pressure you are getting this, and this value moment about major axis divided by sectional modulus 8.51. Moment about the minor axis divided by sectional modulus 13.04, and final maximum pressure we are getting 344.38 and minimum pressure 301.28. so this maximum pressure is less than of your SBC of the soil. SBC is what? 375. so your maximum pressure is less than of your SBC plus your minimum pressure is more than of 0, so both criteria is not going to be satisfied. That's why we are going to say it is what? Passing. So in the second trial, the calculated maximum pressure 344.38 kN per meter square is less than the safe bearing capacity of the soil as 375 kN per meter square. Hence it's safe and the size of the footing is now acceptable. So finally we are going to conclude here that by including the consideration of the movement and by considering the axial load, both the things, we are getting the final safe size of the footing as 2 meter as the width of the footing and 2.3 meter as the length of the footing. Now the next important point is that we have to calculate the ultimate pressure along the length of the footing and along the width of the footing separately. Here the pressure we have calculated, that is what? For the overall, by considering the both direction together. Now we have to do the calculation for each direction separately. So we are going to find out the what maximum and minimum pressure is acting along the length of the footing, what maximum and minimum pressure is acting along the width of the footing, and for that reason here we have given the formula ultimate maximum pressure along the length of the footing and ultimate minimum pressure along the length of the footing. Likewise, ultimate maximum pressure along the width of the footing, ultimate minimum pressure along the width of the footing. So one by one for each direction we are going to do the calculation. So the formula is very simple. Here what we have to consider for one direction at a time. So total pressure plus pressure due to movement. So total pressure, now at this time we have to consider the factor value. So basic service load is 1485 multiplied by 1.5. Okay, so we will get the factored value, and the service movement we have given along the major axis is 15 kilonewton meter. We are going to multiply it with 1.5. So these values are going to become factored value. That's why we are getting the factored upward soil pressure as maximum along the length of the footing. So now we are going to put the value here, that is what? 1.5 multiplied by 1485 divided by total area of the footing with a finalized size of the footing as 4.6 meter. So 4.6 plus 1.5 to make it factor, and the moment about the major axis means mx, we have given it as mx 15 kilonewton meter. So we are going to put it here 15 divided by sectional modulus about the major axis. So sectional modulus about the major axis 1.76. So 1.76 with the final size of the footing as 2 meter by 2.3 meter. So here what value we are getting? Maximum pressure 497 kilonewton per meter square. We are going to write it here. Maximum pressure along the length of the footing 497. Likewise, same calculation for minimum pressure, you just only have to subtract this value. Okay, so total pressure minus subtracting the pressure due to movement, we will get the minimum pressure 471. We are going to write it here. In the same way, we are going to do the calculation along the width of the footing. So along the width of the footing, the moment about the minor axis we need to consider. So here what is going to become? Basically P divided by A plus My divided by Zy, that is nothing but the sectional modulus, and don't forget to multiply with 1.5 to make it a factored value. So we are getting 503 kilonewton per meter square, and minimum value we are getting 464 kilonewton per meter square. So both the values we are going to write here. 503 and 464 is your maximum and minimum pressure along the width of the footing. Hope that's clear to all of you. Now let's talk about the design for the flexural reinforcement in the step 2. So we first actually have to calculate the moment along the length of the footing. Thereafter we have to do the calculation of the moment along the width of the footing. Without of calculating the movement along the length and width, you cannot do the calculation for the reinforcement demand. So very first thing, we need to calculate the moment at the face of your column along the length. So we have the length of the footing as 2.3 meter and width of the footing as 2 meter. So very first we need to calculate this projection, how this projection is coming from the face of your column. So that's very simple. That is what total length, that is 2.3 divided by 2. So you will at the center. Now you also have to subtract the half of your column depth. So column depth is 0.6 meter and half of that, here 0.6 divided by 2. If you are going to do this calculation, you will come to know what is the projection. So projection will be 0.85. Or other way how you can calculate this projection, that is very simple. 2.3 minus depth of the column 0.6, this to be divided by 2. If you are going to divide this value by 2, you will get the projection as 0.85. So how this value is coming, I have explained. Now we already have calculated the maximum pressure along the length and minimum pressure along the length. If you are going to see the previous calculation, so maximum pressure 497, minimum pressure 471. So I am going to write it here again, the same thing, 497 and 471. So we are having the pressure value at the edges, at this and at this, but we want to calculate the pressure value or intensity of the pressure at the face of your column. So this intensity of the pressure we need to calculate. This is our objective. Without of calculating the pressure at this face of your column or at this section, you cannot proceed for calculation of the moment. So for this, what we are going to do, we are going to define it as A and B. Means this height we are going to define it as A and the remaining we are going to define it as what? B. So A will be your 471 and B will be what? B will be 497 minus 471. You will get the value of B, that is going to become 26. So we are having total A 471 and B 26. If you are going to add A plus B, you will get the total 497. That is very simple. Now we have to calculate this total height. But this total height, if suppose you are going to calculate, so this part we already knowing, that is nothing but 471. Only the problem for this part, from this point to this point, this part is only in question. We have to calculate this height. How you can calculate this height? Very simple. We can use the concept of similarity of the triangle. With the help of the similarity of the triangle, we can calculate the B1 value. So simple concept is there. That is what we are going to consider this triangle, and what will be there? Height of your big triangle and base of this big triangle. What is the height of this big triangle? That is nothing but 26. So 26 divided by base of this big triangle, that is nothing but 2.3 meter total length of the footing, equal to height of the big triangle, base of the big triangle. Now height of the small triangle and base of the small triangle. So height of the small triangle, that is nothing but B1 divided by base of the small triangle, that is going to become 1.45. How you can calculate this? Projection plus depth of the column. If you are going to add the depth of the column in your projection value, you will get this value. Okay, so I am going to put this as 1.45. If I am going to take 1.45 on this side, Okay, in multiplication, so this formula you will get B1 will equal to 26 divided by 2.3 multiplied by 1.45. And guys, after doing this calculation, you will come to know the value of B1 16.39. Here also it is mentioned. Now finally, at the proposed section means at the face of your column, what will be your total height? Now it is going to become A plus B1. Here it was A plus B. Now here it is going to become A plus B1. So A plus B1 is going to become, A is your 471 plus 16.39. It is going to become 487.39 kilonewton per meter square. So it is what total height at the proposed section for the upward soil pressure distribution diagram. Now we are going to take this entire section separate. So we are going to take it outside. So total height at this section 487.39 we already have calculated here, and this is the total height at the edge 497. Now we have to do the movement. Our objective is not to calculate A, B, C. That is not our objective. Our objective is to calculate the movement at the face of your column. So now we are taking this part separate, and I would like to give the naming to this part as A1 and A2. Why I am going to give the name as A1, A2? Because it is trapezoidal shape. So we want to make it in two different parts of well defined shape as rectangular and triangular. So this rectangular part we are going to call it as A1, and this triangular part we are going to call it as A2. And then we are going to do the calculation with reference to these areas as the movement at the face of your column. So how we can do this? A1 will equal to the area of this footing. How you can calculate the area of this footing? That is very simple. What is that? 0.85 is your projection multiplied by height, total height 487.39, and this is going to be distributed over the width of the footing. We are going to do the calculation along the length. This pressure is going to be distributed over the width of the footing. So we are going to multiply with width. Here we need to put here as width. So if you are going to do this calculation, we are getting the area 1 828.56 kilonewton. Second, area A2, that is what? Triangle. So triangle formula you know very well. Half base is what? 0.85 multiplied by this height, triangle height. How you can calculate this? 497 minus 487.39, and this again to be multiplied with the width of the footing. So finally we are getting the A2 value as 8.16 kilonewton. These areas actually in kilonewton. So how to do this calculation? You got it. Now finally we have to calculate the movement, as these areas is actually as force. We have to multiply with the perpendicular distance. So what perpendicular distance we have to consider? Centroid of these areas. So area 1 centroid will be what? At this point, which will be at half of this. Half of this means what? 0.85 divided by 2. Okay, from the face of your column. So 0.85 divided by 2, that will be the centroid of this rectangle. So basically A1 multiplied with projection divided by 2. So the movement due to the area 1 we are going to calculate, plus movement due to the area 2. So area 2 is not a rectangle, area 2 is the triangle, and you are going to measure the distance of the centroid of the triangle from the angle side. So from the angle side the formula is going to become 2h by 3. If the same calculation if you are going to do from the perpendicular side, then the formula will be what? H by 3. but if we are going to do the calculation from the angle side, so it is going to become 2h by 3. So A2 area we already have calculated 8.16 multiplied by 2h. 2h means this is what h, that is nothing but your projection 0.85. Okay, CLL means the projection along the length of the footing. This is what CLL, projection along the length of the footing, and this will be what projection along the width of the footing, CBB. When we will do the calculation along the width, then we will denote it by CBB, and as we are doing the calculation along the length, that's why we are denoting it by CLL, that is nothing but the projection along the length of the footing. Okay, so 2 times the projection divided by 3 means 2h by 3. Okay, after doing this calculation or after putting all these values in this formula, so it is going to become what? A1 828.56 multiplied by projection 0.85 divided by 2 plus 8.16 multiplied by 2 times again projection 0.85 divided by 3. After doing this complete calculation, we will get the ultimate moment 356.76 kilonewton meter. This was our objective, to calculate the movement at the face of your column along the length of the footing. Hope that it's clear to all of you how to do the calculation of the movement along the length of the footing at the face of your column. Now the same calculation we are going to repeat for calculating the movement along the width of the footing. So very first thing, again we need to calculate the projection, and this projection we are going to denote by CBB, means the projection from the face up to the edge of the footing along the width of the footing. So very simple it is to calculate total width minus width of your column divided by 2. If you are going to do this calculation, you will come to know what is the projection. So we have done the calculation and we are knowing the value of the projection from the face of the column up to the edge of the footing along the width is 0.885 meter. Now we again have to calculate the intensity of the pressure at the face of the column along the width of the footing, and we already have calculated the maximum pressure and minimum pressure along the width of the footing in our previous step. If you are going to see here, we already have calculated the maximum pressure and minimum pressure as the ultimate values along the width 503 and 564. So the same values we are going to put here as 503 and 464. These are the values. Our intention is to calculate the intensity of the pressure at the face of the column. So we need to calculate this pressure height, and how this value can be calculated, we have to take the help of the values from the edges. So at the edge we are going to denote it by A and B. So A is 464 and this B will be equal to total 503 minus 464. So we are getting the B value as 39. If you are going to add A and B, you will get the total height as 503. Very simple it is. Now objective is to calculate this height. So amongst this total height, we already knowing this height. How much it is? It is 464, and the rest we are going to denote it by B1. Again the same concept we have to apply, that is nothing but your similarity of the triangle. So big triangle height, that I am going to represent here as what? B. What is the B? B is 39. 39 divided by big triangle base. Total width of the footing is 2, that is what? Divided by 2, as equal to small triangle height, that is nothing but B1 divided by small triangle base, that is what? Very simple, 0.885 plus 0.23. So you will come to know what is this span. That is nothing but 1.115. If you are going to add this two value 0.885 plus 0.23, you will come to know the total length, this length is going to become 1.115. You can check it. Now this value we are going to put on this side in multiplication, so you will have this value. Okay, B1 will equal to 39 divided by 2 multiplied by 1.115, and after doing this calculation you will have the value of B1 as 21.74. But our objective is to calculate this total height. So how you can get this value? So A plus B1, you will get the total height. So here A plus B1 464 plus B1 is 21.74. So total is going to become 485.74. This value we are getting, and we are going to put here as 485.74. We are going to take this section outside. Okay, we are going to deal it separately, so that's why we are going to represent it here 485.74, and at the edge it is 503. And again this entire area is going to be divided into two areas as A1 and A2. So A1 will be what? This projection 0.885 multiplied by this height, means this rectangle area we are going to calculate. So this is nothing but your area multiplied with the length, because we are going to do the calculation along the width. So along the width, and this is going to be distributed over the length. Remember, so we are going to put here as what? 2.3, because length of the footing is what? 2.3. So after doing this, we are getting the value 988.72 kilonewton. Likewise, area 2 will be what? 1 by 2 base is again your projection 0.885 multiplied by this triangle height. How you will get this value? 503 minus 485.74. Okay, so you will have this area 1 by 2 base into height multiplied by length over which it is going to be distributed. So 2.3 is the length of your footing. Now we are getting the area 2 as 17.56 kilonewton. It is what? Representing in kilonewton. Now finally our objective is to calculate the movement. So the movement at the face of the column along the width. By mistake here it is written as length, but it is actually what? Width. So we have to consider it as what? Width. We will correct it. Okay. Now ultimate movement will be equal to A1 area 1 multiplied by the centroid. Centroid will be what? Half of this projection along the width divided by 2 plus 2 A2 multiplied by centroid. Again we are going to do the calculation from the angle side. So 2h by 3, h is nothing but your projection, CB B divided by 3. So after doing this entire calculation by putting all the values here, we are getting the ultimate movement at the face of your column along the width of the footing as 447.87 kilonewton meter. So this is our final movement along the width of the footing, and previously we have calculated the final movement along the length of the footing. Along the length 356.76 and along the width 447.87 kilonewton meter. So finally we have calculated the maximum ultimate movement at the face of your column in both of the direction. After doing the calculation for the movement along the length and width, we are going to do the calculation for the depth required for the footing. So we have to consider the maximum movement among these movements along the length and movements about the width. So we are having two movements, 356.76 along the length and along the width 447.87 87. So we have to consider maximum of these two to calculate the depth of the footing required for flexure. So we are going to consider the maximum as 447.87 here as the maximum moment, and the considered width will be 2.3 meter. Okay, so because it is what along the width of the footing, and we have to consider the length. Okay, so here length is 2.3 meter, so depth required will equal to square root of ultimate moment divided by 0.133 fck. B means the width considered for the considered direction. So this movement is along the width, okay, and its length is 2.3 meter. So we are going to put here as 2.3 meter in mm, so that is going to become 2300. So if you are going to do this entire calculation, you will get the depth required as 220.91 in mm is the effective depth required for this footing. Now we have to consider the clear cover. Clear cover for the footing, you know very well, we are considering it as 50 mm, and the diameter of bar we are going to consider it as what, 12 mm. So clear cover as 50 plus half of your diameter of the bar, that will give you effective cover. Okay, so the effective cover will equal to 56. 50 plus half of your diameter is 12, so half of 12 is 6, so 50 plus 6, it is going to become 56 as the effective cover. After this, what next? We need to calculate the overall depth required. So overall depth will be equal to effective depth plus effective cover. Effective depth 220.91 plus 56, it is going to become overall 271.91 in mm. Now to be on safer side, providing the overall depth as 650, you have a question how we can consider directly as 650 as the demand is what, 271.91. So basically this is the depth required for flexure, but in actual the depth requirement is going to be governed by the shear criteria. Your foundation depth is going to be decided based on the two criteria. One is the flexural criteria, another one is your shear criteria. Shear, you know, one way shear check, two way shear check. So normally the depth of the footing is going to be decided by the shear criteria, not by the flexural criteria. Flexural demand will always be less in comparison of the shear demand. That's why in advance, for the sake of safety, we are going to take overall depth as 650. Later on, if it is failing, we will increase it. If it is coming out to be over safe, we will reduce it. So it is what, trial overall depth you can call it too. Okay, so overall depth as 650 mm. Now finally we have to calculate available effective depth. Effective depth available will equal to overall depth 650 minus overall effective cover. Effective cover is what, 56. So 650 minus 56, we will get the effective depth as 594 in mm is your effective depth. Now finally we are going to do the calculation for the reinforcement. So reinforcement along the width of the footing. So this is the separate calculation along the width. Thereafter we are going to do the calculation along the length. What reinforcements are required? So along the width, what is the maximum moment? We just have taken the moment along the width 447.87. Along the width, the moment is this one, and this length to be considered, okay, cross length. So here while doing the reinforcement along width of the footing, so I am going to put here as moment 447.87 kilonewton meter, width, cross width 2300 mm, and effective depth 594 in mm. Area of steel required will equal to 0.5 FCK. This is nothing but your FCK divided by your FY, yield strength of the steel, inside bracket 1 minus 4.6 mu, ultimate moment divided by FCK, this is the width as B, and this is nothing but the depth square. Okay, BD square, depth is what? 594, and again it is B into D. B is what? 2300, and depth is what? 594. If you are going to put all the values here, you will get the reinforcement in demand as 1772.5 in mm square. This much area of the reinforcement required for resisting this movement, this flexural movement. AST minimum area of the reinforcement to be provided as per the codal recommendation, that should be 0.12% over the length and overall depth. So it is coming out to be 1794 mm square. So you have to compare these two values, okay, and whatever the value you are getting as maximum, that you have to consider. So we are getting the maximum value as what? 1794 is the maximum value, means demand is less than of the minimum value. That's why we are going to provide at least the minimum value 1794 mm square. Now finally we are going to provide 12 mm diameter of bar, who is having the unit area 113.09 mm square. This is the unit area of 12 mm diameter of bar. So I am going to calculate what spacing is required. So unit area divided by total area we have decided to provide, multiplied by over the considered length, because this entire calculation we are doing along the width. But guys, try to understand, this reinforcement is going to be distributed along what? It is going to be distributed over the length, remember. So everywhere we are considering as length, because it is going to be distributed over the length. So 2300, when we are doing the calculation along the length, then we have to consider the width, because it is going to be distributed over the width. But as of now we are doing the calculation along the width, that means it is going to be distributed over the length. So 2300, after doing this we are getting the spacing to be provided as 144.99 in mm. Now we are going to provide the spacing finally as 125 mm center to center. This is the final spacing I would like to provide here. So finally, what area of the reinforcement you have provided, finally we need to calculate that, because with this area of the reinforcement 1794, the demand of the spacing was this. Okay, now we have changed the spacing, so obviously the area of the reinforcement provided will also going to be updated. So here unit area divided by finally provided spacing over the same length. Now total area of the reinforcement finally provided 2080.85 mm square. Now we have to calculate the reinforcement in percentage by considering the overall section. So total area provided divided by total length over which the reinforcement is going to be distributed, and overall depth. So we are getting the percentage of reinforcement as provided as 0.139%. So reinforcement along the width of the footing is 12 mm diameter of bar at a spacing of 125 mm center to center. In the same way we are going to do the calculation along the length of the footing. Reinforcement along the length of the footing. Now movement along the length of the footing 356.76, B is 2000 in mm, and effective depth is same 594 in mm. Again you have to put the values here in this formula. This is 0.5, this is the FCK divided by FY, this is your FY, and 4.6, this is the MU divided by FCK, B D square, this is your D square, and it is what? Again B, and it is again D. If you are going to put all the values in this equation, you will get the area of the reinforcement required along the length of the footing is 1409.25 in mm square. Minimum area of the reinforcement 1560 in mm square. So obviously your minimum is more than that of the required one, so we have to follow the minimum one, 1560 mm square, and we have to calculate the spacing required. So we are going to do the calculation 113.09 divided by 1560 over the considered width 2144.98 in mm, hence providing the spacing as 125 mm center to center. Now unit area divided by provided spacing, the length over which the reinforcement is going to be distributed. Now at this time we are doing the calculation along the length, but the reinforcement is going to be distributed over the width. So we will put here as width. So total area of the reinforcement is provided 1809.44 mm square, and by percentage, total area divided by section size, total area divided by considered width 2000 multiplied by overall depth 650, it is again coming out to be 0.13% reinforcement. And finally we are going to write here as reinforcement along the length of the footing, again 12 mm diameter of bar at a spacing of 125 mm center to center. So this is what the reinforcement we have calculated along the length and width. So along the width 12 at 125 and along the length 12 at 125, means in both of the direction we are getting the same reinforcement demand, 12 mm dia at a spacing of 125 mm center to center. After the complete design for the flexure, now the next step is that we have to do the check for one-way shear and two-way shear. So basically whatever the size of the footing as length and width and depth of the footing and the reinforcement that we have provided, we have to check that whether all that designs are safe or not in respect of the shear demand. So that's why we need to perform the one-way shear check and two-way shear check. So we are going to perform first one-way shear check along the length of the footing. After that we have to perform the one-way shear check along the width of the footing. This will be similar to that of the case for the flexure design. At that time we did the calculation for both of the direction separately. In the same way here also the one-way shear check we need to perform for both of the direction separately. So one-way shear we need to perform at a critical distance that we are considering at a distance of d from the face of your column. This is what your critical section for one-way shear. So how you can calculate this span? This span is very simple to calculate. You are having the projection 0.85 minus this effective depth 0.594. If you are going to do this calculation, you will get this value 0.256. And if you would like to calculate this value, how you can calculate it? It's very simple. 2.3 minus 0.256. Okay, if you are going to do this calculation, you will have this value. And at the same time again we have to draw the pressure distribution diagram, which is having the maximum pressure at this edge, minimum pressure at this edge along the length of the footing. We already have discussed over this point earlier how to draw this pressure distribution diagram. And we have to calculate the intensity of the pressure at a critical section, because our proposed section is at a distance of d. So we need to find out what intensity of the pressure at this section. And for that reason we are already knowing this height A. Now in that A we have to add B1 value, so you will have total intensity at this proposed section. But for this we are going to say this height as A, and this remaining height on this side we are going to call it as B. So B is very simple to calculate. B will equal to total 497 minus your A value, that is 471. This calculation here it is already given, so A and B you can easily calculate. Question is to calculate the B1 value. How you can calculate this B1 value? By the similarity of the triangle. This is our triangle. and this triangle we have to consider this big triangle height, big triangle base. Okay, so big triangle height is what? 26. Let me show here. B, okay, 26 divided by big triangle base, that is 2.3, is equal to a small triangle height, that is B1, divided by a small triangle base, that is 2.044. Now this value will come on this side, and finally we are having our B1 value 23.106. Adding this B1 and A together, we will have final intensity at our proposed section, that is nothing but 494.106 kilonewton per meter square, because it is the upward soil pressure. Now we are going to take this entire area outside and we are going to denote it by A, and we have to calculate the area of this trapezoidal, and we have to distribute over this span. So 1 by 2 base height, this height 497, this height 494.106, this two to be added, divided by 2 means 1 by 2 multiplied by this 0.256. If you are going to multiply this, you will get the intensity of the pressure as distributed 126.86 kilonewton per running meter. Now finally we had to calculate the shear force at the critical section. So very simple, this value is needed to be multiplied with the width of the footing, because we are doing the calculation along the length, and this is going to be distributed over the width of the footing. So width of the footing will also have to be considered, so that's why we are going to multiply it with 2. So finally have a look over the unit, kilonewton per running meter multiplied by with meter. Meter will get cancelled. You will have the shear force value as 253.72 kilonewton. Now nominal shear tau v will equal to Vu upon B into D. It is a very famous formula, you all know very well how to use it. So put the value of shear force divided by B is 2000, effective depth 594, so you will have your nominal shear value 0.21 due to this shear force. We have to calculate what is the capacity of your section for resisting the shear, and that is going to be denoted by the critical shear tau c. So we have to calculate what is the capacity of our section, that is tau c, and for that reason we need to have the percentage of steel and grade of your concrete FCK. So both of the things we are having. So percentage of reinforcement we have provided along the length of the footing as 0.139. I can show you when you are going to see the reinforcement along the length of the footing. So the length of the footing, the reinforcement is available as 0.139 percentage. So I am going to put here as 0.139 percentage, and characteristic strength of the concrete is what? 30. We have to look at IS 456-2000 table number 19, the value of the critical shear for the percentage of the reinforcement less than of 0.15%, and for the M30 grade of concrete it should be considered as 0.29. Have a look over the IS 456-2000 page number 73 table number 19. So if your percentage of reinforcement is less than of 0.15%, because our percentage of reinforcement is what? 0.139, and for M30 grade of concrete it is 0.29. So I am going to put it here as 0.29 critical capacity. So nominal shear is 0.21 and critical shear is what? 0.29. So critical means your capacity. So capacity is more than what action is there, what loading is there. So nominal shear is less than of your capacity, hence it is safe. So provided depth is safe for one-way shear along the length of the footing. So along the length of the footing the design is completely okay. Now the same calculation we are going to repeat for the width. So again have a look over this. We are going to consider the one-way shear section at a distance of D from the face of your column. So along the width we are having the projection 0.885. So 0.885 minus effective depth, that is 0.594. Okay, so if you subtract 0.594 from 0.885, you will get this value 0.291. And if total width means 2 meter minus 0.291, if you are going to do this calculation, you will have this span 1.479. Next to this, we have to draw the pressure diagram. Here again the pressure diagram is available, and we know phi naught 3 and is 464 maximum pressure along the width, minimum pressure along the width. Maximum pressure we are going to break into two parts, A and B. The height up to this level we are going to say A, and the height next to this we are going to call it as B. So B is very simple to calculate. A is 464, B will equal to phi naught 3 minus 464. So it is going to become 39. Now we have to calculate B1. B1 we have to calculate from here to here and this. Okay, how to calculate? You know very well, many times we already have discussed. We have to use the similarity of the triangle. So by the similarity of the triangle, you will have the value of B1 28.84, and finally by adding this A and B1 we are having 492.84 kilonewton per meter square as the upward soil pressure at a critical section at a distance of D from the face of your column. Again we have to calculate the area of the trapezoidal. So have a look over this. Phi naught 3 plus 492.84. So 1 by 2 phi naught 3 plus 492.84. It is to be distributed over this base 0.291. So we are having the intensity of the upward soil pressure 144.89 kilonewton per running meter of your width. So now we are going to multiply this width. Width means what? This width. This is the width of the footing or the direction of the calculation, and perpendicular to this the span is what? Your length. So we have to multiply it with length. So I am going to put here as 2.3. If you are going to put here as 2.3, so finally we are having the value of the shear force 333.25 kilonewton. This is the shear force at a distance of D for the one-way shear check along the width of the footing. Now simple again, nominal shear VU upon BD. Shear force value you have to put here. B value now it is going to be changed as 2300 will be there, and 594. Finally we are having the nominal shear 0.24 Newton per mm square. After all of this, the percentage of reinforcement available along the width of the footing again 0.139 percentage. If you are going to see the previous calculation, reinforcement along the width of the footing, so percentage of the reinforcement available along the width of the footing 0.139. So the same percentage of reinforcement we are going to use here 0.139 as per IS 456 2000 table number 19. If the percentage of reinforcement is less than a 0.15 and if the grade of concrete is M30, we already have seen in our previous check, if your percentage is less than a 0.15 and grade of concrete is M30, the critical capacity of the shear will be what? 0.29. So we are going to put here as 0.29. Again your nominal shear is 0.24 and your critical capacity is 0.29. Hence again we can say that provided depth is safe for one-way shear along the width of the footing. Last time we have performed the check along the length, now we have performed the check along the width. So in both of the direction the one-way shear check is safe. Now after the completion of one-way shear check for both of the direction, we have to perform the check for the two-way shear, or sometime we are calling it to punching shear. So we have to consider a critical section at a distance of D by 2 from the face of the column in all the direction. If you are going to see this figure, so this is the punching shear check figure, and in this case we have to calculate the shear force value at this section, and this section we are going to consider at a distance of d/2 from the face of the column in both of the direction, along the length of the footing as well as along the width of the footing. So our objective is that what we need to find out the what shear force value is acting at this point, and due to that shear force value means the ultimate shear force value, due to this ultimate shear force value what shear stress is going to be developed at this section, that we are going to denote by tau v. So this calculation is needed to do, and for that reason we have to go through the formula. So first we need to find out the maximum ultimate pressure. So maximum ultimate pressure will be equal to 1.5 times overall maximum upward soil pressure. Now how this value is coming, let's try to understand. When we are doing the one-way shear check, so one-way shear check we have performed for each direction separately. One-way shear check along the length of the footing, one-way shear check along the width of the footing. But when you are going to perform the two-way shear check, so two-way shear check is going to be performed overall the footing area. It is not going to be considered for a specific direction as we did for the case of your one-way shear. But in case of two-way shear we are considering the overall footing, and that's why we have to consider the overall maximum pressure. When we are performing the one-way shear, what we are looking at, we are looking at the maximum pressure along the width, minimum pressure along the width. When we have performed the check for the length direction, so what we have considered the maximum pressure here, minimum pressure here. But now for the case of two-way shear, again I am repeating, we are going to consider the overall footing. That's why we should have to consider the overall maximum pressure, and that overall maximum pressure we already have calculated in a very first step. Let me show you in the table when we have decided the final size of the footing. In our second trial we were finalized our final size of the footing as 2 meter by 2.3 meter. So with this size we already have calculated the maximum pressure, overall maximum pressure. Okay, it is not specific to a particular direction, it is the overall pressure. And if you are going to see this figure, this is the maximum pressure for the length, it is the minimum pressure for the length, it is the maximum pressure for the width, it is the minimum pressure for the width. But we want to have the maximum pressure as overall, that's why we are going to consider it is the maximum overall pressure 344.38 kilonewton per meter square. So this maximum upward soil pressure value we should have to use for checking the punching shear value. Now putting the value here, 344.38 multiplied with 1.5, you are finally having the ultimate maximum upward soil pressure as 516.57 kilonewton per meter square. So this is basically the pressure. We want to have the shear force value which is going to act at this section. So how you can calculate this? So the upward soil pressure is needed to be multiplied with this empty space, this empty area. So how you will come to know what is this empty area? Very simple. You have to find out the total area, 2 meter by 2.3 meter, and then you have to subtract this shaded area from this total area. So you will have this empty space area. Okay, this outside area you will get. So this calculation here it is already given. I can show you. This is the upward soil pressure multiplied with total area minus shaded area. Okay, so upward soil pressure 516.57 kilonewton per meter square, total area 2 meter by 2.3 minus this shaded area. How you can calculate this? So first you need to calculate this width, you need to calculate this length, and you need to calculate this width. So it is d by 2. On this side also d by 2. So d by 2 is going to become what? D. And this is your depth of your column. So depth of your column plus d is your actually the length of this internal shaded area. The width of this shaded area will be simple, width of your column plus d. If you are going to multiply these two value, you will have the area of this shaded portion. So that thing we have calculated here, total area minus the shaded area, and this entire value should be multiplied with 516.57. so you will have your shear force value 1867.99 kilonewton. So now you are having your shear force value. Thereafter we have to calculate the perimeter length of this shaded area. How you can calculate it? Again, it is very simple. This is your length, so depth of your column plus d by 2 on this side, d by 2 on this side. So this term here it is present, so we are getting this span, but it is not one time, it is two time, this side and this side. That's why it is going to be multiplied with 2. This value to be added with 2 times width of this shaded portion. So this width of the column plus d by 2 from this side, d by 2 from this side, it is again going to become d. So width of the column plus d. So BC plus d by 2, you can call it to directly as d, and this to be multiplied with 2 because here it is also present, here it is also present. So we are finally having the perimeter length of your shear area, and we are going to denote it by d dash. So after doing all of this calculation, we were come to know that what is the perimeter length of this shaded area? 4036 mm. Now finally we have to calculate the nominal shear at this critical section, and that we are going to denote by tau v. Tau v will equal to Vu upon b dash d. So b dash is your perimeter length of your shaded area, and d is your effective depth of your footing. Now finally, taking all the values in this formula to calculate the value of tau v. So Vu we already have calculated. Vu is equal to 1867.99 kilonewton. So we have to put the value of Vu in Newton. So that's why 1867.99 into 10 raised to 3 divided by b dash. B dash is nothing but your perimeter length multiplied by your effective depth. After doing all this calculation, we were getting the value of tau v as 0.7791. Now we have to compare this nominal shear value with your critical shear value. So what is the critical shear value? How you can calculate the critical shear at your critical sections for the punching shear? As per IS 456 2000, page number 58, clause number 31.6.3, shear at the proposed critical section should be calculated with this formula. Where it is given? It is given in your IS 456 page number 58, clause number 31.6.3.1. So the critical shear value should be Ks into tau c. Now tau c we can easily calculate. There is a question for Ks. So how you can calculate the value of Ks? Ks will equal to 0.5 beta c. And what does mean the beta c? Beta c is the smaller side of your column divided by longer side of your column. This ratio will give you the value of beta c, and that beta c value you have to add into 0.5 value, and this value should not be more than of 1. If this case value is coming out to be more than of 1, you are limited to take the value of Ks to a maximum of 1 only. Although it is coming more than of 1, then you are only limited to take it as what? 1. And if the value of Ks is coming out to less than of 1, then you have to carry the calculated value of Ks. Remember this point. It's very simple. Now coming back to the calculation, and we would like to calculate the value of Ks. So Ks will equal to 0.5 plus beta C. Beta is the shorter side of the column divided by longer side of the column. Your size of the column is 230 by 600. So 230 shorter divided by 600 longer. We are getting the value of beta C 0.3833. Now this value is needed to be added with 0.5. After doing this calculation, we are getting the value of Ks as 0.8833, which is less than of 1. Now finally tau C will equal to Ks into 0.25 under root of FCK. It is nothing but your critical shear value. So 0.833 multiplied by 0.25 under root of FCK, our grade of concrete is what? 30. That's why we are going to put the characteristic strength of our proposed concrete here. Now finally we are getting the value of tau C as 1.2095 MPa. Now finally we have to compare critical shear with your nominal shear. Nominal shear we already have calculated here. Where is the nominal shear? Nominal shear 0.7791. Now I am going to see tau V nominal shear 0.7791, which is less than of critical shear 1.2095. Hence it is safe to punch. Your provided depth of the foundation is safe for the punching. Your foundation is not going to be failed under the punching shear check. So in this way we have to perform the punching shear check. Up to this level we have completed all the calculations and all the designs as per the problem statement A. In our problem statement A, we have stated that we have to design the foundation. We have to find out the size of the footing as width, depth and everything. And we also have to find out the flexural reinforcement. We have to find out the shear stresses values and have to check for the one-way shear and two-way shear. Everything we have completed as per the recommendation from the problem statement A. Now we have to look at problem statement B. What is the recommendation of your problem statement B and what to do according to problem statement B, we will see that. So the foundation that you have designed in above case, it is having the depth as 2.5 meter, means the foundation base is available at a depth of 2.5 meter from the ground level. This is what given in your problem statement B. While the groundwater table lies 5 meter below the ground level, but your water is also present at a depth of 5 meter from your ground level. This is the second thing. And the third thing, we have given that the unit weight of the soil is 18 kilonewton per meter cube and the coefficient between the base of the footing and the soil, that is the frictional coefficient, is 0.5. A service lateral load of 45 kilonewton acts at the ground level. At the ground level there is a presence of lateral load as well. In our problem statement A, we have not given all this data. As per our problem statement A, our footing was subjected to only the gravitational load. There was no any presence of your lateral load. But if you are going to see the part B, in your part B there is a presence of two things. Two new things are there. One is your water level below the foundation and lateral load, that is nothing but 45 kilonewton, which is acting at the ground level. Why these two things, and along with this the frictional coefficient is also given. So why these all things has given, we have to understand that. Actually we have to perform the stability checks. What does mean the stability checks? Stability checks means under all of these circumstances, under all of these situations, whether your foundation will be safe or not. Due to uplift, due to sliding, due to overturning, under all of this situation, whether your footing is safe or not, we have to check that, and that checks is called as what? Stability checks. and these all stability checks is not needed to be performed under the factored load. It is needed to be performed under the service load, because it is a service stability check. It is a stability check. Keep in your mind. So very first we are going to perform the uplift check. What does mean by the uplift check? Try to understand. When there is a presence of your footing plus there is a presence of the water which is close to the base of the footing. So what is happening? This water is going to impose the pressure at the base of your footing, and due to this pressure your footing may get lifted, and that is not recommended, that is not acceptable. Your footing should not be lifted. So we have to see that whether the presence of this water is going to cause instability of your footing, which you have designed in your problem statement A case. So we have to check that. So first you need to find out the what is the depth of water actually, because we have given the total depth of the water from the ground level. So water depth below the base of the footing will equal to total depth minus depth of your footing base. So after doing this calculation we were seeing that 2.5 meter is your depth of the water below the base of the footing. Now we have to find out the upward pressure due to water, not due to soil, remember. So unit weight of the water multiplied by height of water. After doing this we are getting the pressure due to water is 25 kilonewton per meter square. Total uplift force. So this uplift force, uplift pressure, where it is going to act? It is going to act overall the area of your footing. So we have to multiply this upward water pressure over the area of the footing. So we are getting total uplift force. Total uplift force will be equal to uplift water pressure 25, we have calculated this, multiplied by total area of the footing 2 into 2.3 meter is our size of the footing. So if you are going to multiply these two things, you are getting the upward water pressure at the base of your footing. So 115 kilonewton. Now it is causing the instability. Now what other thing is there which is causing the stability? Self weight of the footing plus the load. Here see, we have to calculate the self weight of the footing. Self weight of the concrete footing, overall depth of our foundation is what? 650 mm. So in meter it is going to become 0.65 multiplied by total area of the footing multiplied by unit weight of your concrete. Concrete is what? Having the unit weight 25 kilonewton per meter cube. You have to multiply all of these values. So what we are getting? We are getting what? 74.75 kilonewton is the self weight of the footing, plus this part will be what? Filled with soil, and that is going to be called as overburden. Overburden pressure we are going to call it as sometime, or overburden load we are going to call. So overburden soil 5 meter above the water table. So above the water table, this is the water table. So this total height we have to consider. Not only this height we have to consider, we have to consider this total height. Okay, 5 meter. So this is entirely filled with soil, and thereafter the water will be present. So basically 5 meter multiplied by 4.6 is the total area multiplied by unit weight of your soil. If you are going to multiply all of these things, we are getting the total overburden soil weight as 414 kilonewton. Now finally the load which is acting in downward direction, that will be 74.75, 414 kilonewton. If you are going to add these two value, you will get the total downward force 488.75 kilonewton. It is a downward force, and there is a uplift force also present, that is nothing but 115. Now we have to check a factor of safety against the uplift. So resistance force means which is acting in downward direction, uplift force which is acting in upward direction. So downward direction 488.75 divided by 115. If you are going to find out this, we will get the value of 4.25, which is greater than of 1.5. Hence we can say that our design or our condition is safe against the uplift. So this is our first check. Now second check is your what? Check for the sliding. As your foundation is going to be subjected to lateral load which is acting at the ground level, and the intensity of the lateral load is what? 45 kilonewton. So in your problem statement, if it is given your foundation is going to be subjected to lateral load, then sliding check is must to do. If the lateral load is not there in your problem statement in your project for your foundation, at that time sliding check is not needed to perform. So lateral force is given as 45 kilonewton. Friction coefficient we have given as 0.5 in our problem statement B. So what is actually going to happen? Try to understand. As your footing is present here with its self weight, with its overburden soil weight, everything is actually present. Now this lateral force will trying to push your footing in this direction. But if your footing is not capable of maintaining its stability, what will happen? Your footing is going to be shifted in this direction, and that is called as sliding of your footing. But we don't want this sliding of the footing. So how you can protect your footing from sliding? You have to provide enough weight of the footing so that it will maintain its position. It is not going to be shifted left or right due to the application of the loading. So that is what possible with enough weight of the footing. So that weight of the footing is going to be multiplied with a coefficient of friction, and this finally the resisting value against of your applied lateral load. So how to do this all calculation? Try to understand. Calculate the vertical dead load or resisting force. Footing weight. Footing weight, how you can calculate? 0.65 is the overall depth of your foundation. Area of the footing 4.6 multiplied by 25. This calculation we already have done in our previous case of the uplift check. 74.75 kilonewton. Soil weight above the footing. Now at this time we don't need to consider up to the water level. Water level consideration only for the uplift check. Now here we have to consider only this height 2.5 meter. So 2.5 meter, and plus we have to subtract the depth of the footing. So 2.5 minus depth of the footing, finally we are having 1.85 meter. This is your net height, and the soil present in this net height we have to consider that only. So 1.85 height of the soil above the footing multiplied by area of the footing multiplied by unit weight of your soil. So soil weight we are getting 153.18 kilonewton. So one is your self weight of the footing, another one is your soil weight above the footing. We have to calculate the total weight. Total weight will equal to concrete footing weight plus weight of the soil is going to become 227.93 kilonewton. Now this value we have to multiply with a frictional coefficient. Okay, so that is nothing but 0.5. So I am going to multiply it with 0.5. So 0.5 227.93, we are getting the value of 113.965 kilonewton. So factor of safety against the sliding will equal to resistance force divided by lateral force. Always in your numerator will be what? Resisting value, which is what? Maintaining the stability. And always in your denominator what will be there? The value which is going to create the instability. So lateral force is going to create the instability, and resistance force is maintaining the stability. Okay, so we are getting this ratio as 2.53, which is greater than of 1.5. Now again we can say here safe against the sliding. Your footing is not going to be shifted anywhere even though there is a presence of lateral force of 45 kilonewton. This is the second check. Now third check is the overturning check. What does mean the overturning check? Let's try to understand. So basically, as your foundation is going to be subjected to lateral load at its ground level, and this height is actually present. So if I am going to fix this point, about this fixed point, what will happen? Your footing is going to be what? Rotating in this direction. if your footing is not going to maintain its stability, it is not having enough capacity to resist this movement. So what will happen, due to this lateral force and due to this perpendicular distance, what will happen, the movement is going to act in this direction. Your footing is going to tilt, your footing is going to rotate. So overturning movement, it is going to be called as what, overturning movement. So overturning movement will be equal to lateral force multiplied by height. Okay, from this base point, the height we should have to consider, so that is nothing but 2.5 meter. So we are getting the overturning moment as 112.5 kilonewton. So this is causing what, instability. Now what property is there which is maintaining the stability? Again the vertical weight. Total vertical weight we already have calculated 227.97 in our previous case. How this value is calculated? Weight of the footing plus weight of the soil above the footing, this combinedly giving this value. So now we are having the total vertical weight 227.93 kilonewton. Now resisting moment, how you can calculate the resisting moment? Resisting moment will be what? Actually this point we are going to fix, not this point we are going to fix. We are going to fix what? This point. So in reference of this point, the perpendicular distance to this lateral load is what? Again 2.5. So that is same. There is not a problem with your overturning moment. Overturning moment is correct. Now this self weight of the footing plus weight of the soil is going to act from the center point, and we are going to fix this point. So due to this lateral load, there is a movement in this direction. Try to understand, if I am going to fix this point, if I am going to hold this point, and this lateral load is suppose going to act in this direction, so my footing is going to be what? Tilted in this direction. My footing is going to be subjected to movement in this direction. But there is a presence of the weight, so that weight is acting at this point, and this is the perpendicular distance. So it is the resisting movement in this direction. This is the resisting movement. It is the overturning movement. This is your resisting movement. Okay, which is controlling the overturning movement. So I have to calculate it. Resisting moment will equal to weight, overall weight multiplied by width of the footing divided by 2. We already have seen, we are going to fix this point, and from this point the perpendicular distance will be what? This is the width of the footing. So half of the width of the footing we will get this distance, because we want to have the perpendicular distance from the point where your vertical load is acting. So total weight is going to act from this point. So total weight multiplied by BF by 2. Finally you have to do this calculation. 2 by 2, it is going to become 1. Ultimately you are having the same value, 227.93. basically it is what? 227.93 or 92. That is not going to make great difference. I will correct in the file. Now factor of safety against the overturning. Again resisting moment divided by overturning moment. Resisting moment 227.92 divided by 112.5. This ratio is again coming out to be 2.025 greater than of 1.5. Hence again I can conclude that the design is safe against the overturning as well. So all the stability checks are safe. Your design or stability is safe against the uplift, against the sliding, and against the overturning. So we are going to take the help of this spreadsheet for the effectively designing of this type of foundation in a short period of time. If you are going to do the design by manual approach, it will take hell lot of time. So to save the time, we are going to take the help of this spreadsheet. And for better understanding of the application of this spreadsheet, we are going to take the help of one reference problem, and with the help of that reference problem we are trying to understand the application of this spreadsheet. So without of wasting time, have a look over the problem statement. So the problem statement has given in the two parts. So one by one we are going to understand it. A rectangular column of size 230 by 600 in mm is transmitting a vertical load of 1350 in kilonewton along with the moment of 15 kilonewton meter about the major axis. So here in the figure you can see that the footing is going to be subjected to 1350 kilonewton in a gravitational direction through the column centroid, and there is a movement about the major axis, means the axis which is passing through the width of the column is 15 kilonewton meter, and there is another movement of 20 kilonewton meter about the minor axis, the axis which is passes along the depth of the column. This is what experiencing the movement of 20 kilonewton meter. The footing is to be designed for the materials as M30 grade of concrete and Fe 500 grade of steel. The safe bearing capacity of the soil is given as 375 kilonewton per meter square. The permissible settlement is limited to 25 mm. We have to design this foundation for the given data and the soil condition. This is the responsibility to do. And in the problem statement part B, what is given? The depth of the foundation from the ground level is 2.5 meter. It is what? 2.5 meter from the ground level up to the foundation base. The depth of the water level below the ground is 5 meter. The depth of water level from your ground, it is given as what? 5 meter. The unit weight of the soil is 18 kilonewton per meter cube, over which it is going to be rested. The coefficient of friction is to be considered as 0.5. The service lateral load acting at the ground level is 45 kilonewton. So the lateral load is also acting on this foundation at the ground level is 45 kilonewton. It is the service load. We have to perform the stability checks for uplift, for sliding and for overturning. So basically, in general case, for the normal foundation design, we have given this data just to do the simple design when there is no need to perform the checks, stability checks. But if suppose you want to do the stability checks, so you need to have this data also. Depth of the water table, friction, everything you need to know. So in this spreadsheet you can perform the stability checks as well. This sheet is capable of performing the design, scheduling, detailing as well as performing the stability checks. Now one by one we have to do the steps for the purpose of designing. But before of that, let's try to understand how to use this spreadsheet. So here some guideline has given how to use this spreadsheet. So you have to edit the values only in yellow cells. Wherever the white cells are present, you don't need to do anything in that white cells. There is a green cells, that is the sign of the safety or safe design. There is a orange color cell that will define you the value which is close to safe. That is the suggesting cell. This cell will suggest to you what should be adopted. And wherever you are getting the red cell, that is the cell of the danger. Means you did something wrong, you had to correct that. It is the failure sign. Hope that you all understood how to use this spreadsheet. Now here we have to define the data that we have given in our problem statement. So in the problem statement, the first thing, as the sheet is asking, what is the SBC of the soil? So SBC of the soil, here it is given 375. So I am going to put here as 375. Next to that, what is the unit weight of the soil? So the unit weight of the soil is given in our problem statement as 18 kilonewton per meter cube, as you can find in your problem statement is the unit weight of the soil. Next, it is asking depth of the foundation and water. So depth of the foundation from your ground level, it is 2.5 meter, and depth of the water from the ground level is 5 meter. What is the size of your column? 230 by 600. If any other size of the column is there, that you can define here as suppose 300 by 900 is the size of your column, so that you can define. So here my size of the column is 230 by 600. So whatever the size of the column you are defining, accordingly your figure is going to be updating here. So size of the column is, suppose I am going to define as what, 300 by 600 in mm. So as you can find here, accordingly the figure is now updating here. And if suppose the size of the column is 230 by 600, so accordingly the figure is going to be updating here. So based on your input data, your figure is going to update. Thereafter, what grade of concrete you have to use for the designing of this foundation? So we have to use M30 grade of concrete and Fe500 grade of steel. So I would like to define those things in this spreadsheet. So FCK grade of concrete, so whatever the grade of concrete you would like to use, you can use from here. So M30 grade of concrete, and drop down list is there for choosing the grade of steel. So our grade of steel is what, Fe500, that's why I am going to choose Fe500. Clear cover for the foundation, it is what, always you know very well, we have to define it as what, 50 mm. The diameter of the bar on a trial stage, we can consider it as what, either 12, either 16, either 25, whatever the diameter of bar you would like to use. At a preliminary stage you can choose that. So I am going to take it as what, 12. Thereafter, load definition. Here you have to set the definition of the load. So in our problem statement, here we have given that the axial load over the foundation is 1350 kilonewton, and moment about major axis 15, and moment about minor axis as 20. So both of the things here I am going to define. So 1350 kilonewton is your service axial load, and moment about major axis 15, and moment about minor axis 20. And one more thing, here it is given, that is what, the lateral load. So the lateral load in our foundation at the ground level is going to act with an intensity of 45 kilonewton as the service load. Here it is given in your problem statement as well. So I am going to put here as 45. In most of your cases there will be no any lateral load, so you can put this value as 0. Or even in most of the cases there will be no movement about major axis, you can put it as 0. In most of your cases there will be no any movement about minor axis, you can put it as 0. So whatever the thing is not given, you can ignore that, you can put the value for that particular cell as 0. And if the value is given in your problem statement, then you have to define it here. So this lateral force basically required to do the stability checks only. Otherwise it is not needed to be defined here. But in our problem statement we have to do the stability checks as well, for the uplift, for the sliding, and for the overturning. That's why I need to define it here as 45 kilonewton. Hope that you all understood these things. And you know, at the initial stage we have to consider the self weight of the foundation. So normally we are considering it as 10%. If you would like to change it, like suppose 5%, 7%, 8%, 9%, whatever you would like to do, you can define it here. Accordingly self weight of the footing is going to be considered. So I would like to consider the 10% as the self weight of the footing, so that I am going to define here as. So it is a 10% of your axial load. So 10% of axial load is going to become 135 automatically. So here we are getting gross load and area requirement. We don't need to focus all of these things. We just have to look at what size of the footing is in requirement. So the width of the footing required as 1.81 in meter, and length of the footing required here as 2.18 in meter. But you know, this orange color cell will suggest to you the safe value. So it is suggesting that what width of the footing should be considered, what length of the footing should be considered. So 1.81. So I will try to take it as 1.8, and I will try to take it as 2.2. So what is happening? So it is intimating that your size is inaccurate, which is not safe, because maximum pressure is exceeding the limit of SBC of the soil. Actually the case is what? The maximum pressure should not be more than of your SBC of the soil, and your minimum pressure should not be less than of zero value. So it is safe, and this is what unsafe. So what I need to do, I need to increase the size of the footing. Footing size is unsafe. Here you are getting the status for the acceptance. So what I need to do here, 2.2 I have taken as the sheet is suggested, and thereafter what, here I am going to take it as 2. So whether it is safe or unsafe, yeah, it is now coming out to be safe. Your SBC is 375 and your maximum pressure is 360, which is less than of your SBC of the soil. Now you are safe. If I am going to further increase the size, then it is going to become more safe. So suppose here length I would like to consider as 2.3. Now this is finally the size I am going to adopt. So maximum pressure 344 and your SBC is 375, that's it is safe, and minimum pressure should always be greater than of 0, then what, it is also safe. So if the values are safe, then it is showing by the normal condition white cell, but if it is failing, then what will happen, this is going to be shown by the sheet as red, means sign of the danger. You have to increase the size, and plus there will be no acceptance of the size. But now we have adopted the accurate size, adequate size, so that's why there is an acceptance. So hope that again you are understanding these all things. Now moving ahead, further calculation for the pressure, for the movement, for everything, sheet is going to take care for that, okay. And it is finally calculating the design moment at a proposed section. It is what, along the width of the foundation it is 448.58 kilonewton meter, along the length of the foundation 356.81 kilonewton meter. This is all calculation where the sheet has done accurately, and now we just have to finalize what depth of the foundation we should adopt. So here, as per the flexural requirement, the depth of the foundation is 221.09 in demand. So at least this depth we need to provide for the case of the flexure only. But for your kind information, the depth of the foundation mainly governs for the shear instead of the flexure. There are two types of the demands of the foundation depth. One is your flexural demand, second one is your shear demand. So normally the depth requirement we are going to be governed by shear demand instead of your flexural demand. So instead of directly using 221.09, I would like to go with a 500 depth of the foundation, overall depth of the foundation. So 3 times, as per the expert recommendation, the trial depth of the foundation should be taken as 3 times of the effective depth requirement for the flexure. So if you are going to take 3 times of this 221, 3 times, so it is coming out to be more than of 600. So here I would like to take it as 500 towards a conservative side. Okay, so that's why I am going to define it as 500. Later on, if there is a need to increase the depth, then I will increase, otherwise I will keep it as 500. Now area of the reinforcement required. So here the area of the reinforcement required as 2419 along the width and along the length 1917.34 mm square, the area of the reinforcement required. And what is the minimum area of the reinforcement required, that also given here. Now important thing is that what diameter of the bar you would like to choose. So here I would like to choose the diameter of bar as 16. Here I would like to choose the diameter of bar 20. Here I would like to choose the diameter of bar of 22. So whatever the diameter of the bar you are going to choose, the spacing requirement is going to be adjusted accordingly. But you know, as per our codal recommendation, the maximum spacing allowed is only 300 mm. You are not allowed to provide the spacing more than of 300 mm between the two bars. But most of the professional structural engineers, they are limiting themselves to provide the maximum spacing to 250 mm. Although your code is allowing to provide the spacing up to 300, but for the safety we are providing the spacing to a maximum of 250. Okay, so what to do here? The spacing is exceeding beyond of 361. If I would like to provide here a 16 mm dia, so accordingly the spacing requirement will be, but we don't need to provide this higher diameter of bars. Just I'm trying to explain. So here 12 I'm going to choose. Here also I'm going to choose the diameter of bar as 12. So if I'm going to use the 12 mm diameter of bar, so what spacing required? 107, 117. And guys, in normal cases we are not providing the spacing less than of 100 mm as well. Okay, so the spacing we are providing in between of 100 to 250. So basically, if here I have a chance to reduce the spacing to what? 100, because whatever the spacing is in demand, you cannot provide the spacing more than of that. Always you have to provide the spacing less than of that. So lower value by the round of factor of 25 mm, because 1 inch will equal to 25 mm. It is again the practical thing. So whenever you are going to execute on site, or the site is going to be executed based on your design, so it should be what? Easy to execute. So on site 1 inch will equal to 25 mm. So you have to provide the spacing with a round of factor of 25 mm. So that's why we are going to adopt the spacing as what? 100 mm. Otherwise you will say that sir, you can take it as 105 as well. So no, I am going to provide the spacing as what? 100. And here I would like to take the spacing of what? 100. You will say that sir, we can take the spacing as 110. So 110, that will also be correct, but for the site consideration it will be difficult to execute. That's why we are going to take it as 100. So finally provided bar is 12 mm diameter of bar at a spacing of 100 mm center to center, 12 mm diameter of bar at a spacing of 100 mm center to center. Got it? So provided percentage of reinforcement is going to become 0.226, 0.226. So as per the codal recommendation, the reinforcement to be provided more than of 0.12%. So in respect of that recommendation we are safe. Now we have to perform the one-way shear check along the length of the footing, one-way shear check along the width of the footing. These two checks is needed to be performed, and there mainly we are looking at the nominal shear and critical shear. So maximum critical shear capacity is what? 0.35, and your actual shear is coming out to be 0.45. That's why it is failing. Fail, revise the depth of the foundation. And along the width of the footing, here what is given? The critical shear is 0.35 and your actual shear which is coming on your footing due to the loading is 0.5. So actual loading is more than of your capacity. That's again sign of the failure. So here sheet is intimating that it is failing. We need to revise the depth of the foundation. So what I need to do? I need to increase the depth of the foundation. Now finally I would like to provide the depth as 650. So now 650 is your depth of the foundation we are going to adopt. And guys, important thing, remember here, actual weight of the foundation is 5.54. Actually, when we are initiating the solution for this problem, we have adopted the self weight of the footing as 10%, because at that time we don't have the length of the footing, width of the footing and depth of the footing. To know the weight of the foundation, we need to have the length of the foundation, depth of the foundation, width of the foundation. If these three things you are having, then only you can calculate the actual self weight of the footing. But once you decided the width, once you decided the length, when both of the things has been calculated and depth as well, then you can calculate the self weight of the footing. So the self weight of the footing is 74.75 and by percentage it is 5.54 only, but we have considered as 10%, so we can take it into safety. Otherwise, if you will say that no sir, I will change it, I will make it accurate, so you can consider it as what, 5.55 or 6% as well. So I can consider here as what, 6%, and accordingly you can further proceed, but I don't want to change it. I would like to go with 10% only. Now again we have to look at what diameter of bar is required and what spacing is required. So I would like to go with 12 mm diameter of bar again, and what spacing is required? Spacing requirement is what, here 145 along width as well, along length as well. So I am going to provide as what, 125 along the width, 125 along the length. So 12 mm diameter of bar at a spacing of 125 mm, 12 mm diameter of bar at a spacing of 125 mm center to center. Now here you can check for the one way shear along length, along width. We found that provided depth is safe for one way shear along the length, provided depth is safe for the one way shear along the width. Now after checking for one way shear, we have to go for the two way shear check, or we can say the punching shear check. So here again we are going to see what is the nominal shear. So nominal shear is 0.779 and critical shear is 1.21. So again your design is safe for the punching shear or for the two way shear, because your nominal shear is less than of your critical shear. So provided depth is safe for the two way shear. Now finally guys, we are going to perform the stability checks. So sheet will take care about performing of the stability checks. So uplift checks, here is what, safe again, because the factor of safety against the uplift check is 4.25, which is more than of your 1.5 limiting value. So it is safe against the uplift check. It is again safe against the sliding check. The factor of safety against the sliding check is 2.53, which is more than of 1.5, and factor of safety against overturning check, it is 2.03, which is more than of 1.5. So our design is safe against the all stability checks. And when your foundation is not subjected to lateral load, let's consider an example. I am going to put here as what, 0 value. So you can put it as 0 and there will be no any impact on all of these other design except of only the stability checks. So in your stability checks, the uplift check, it is applicable for every of the cases whether the lateral load is there or not. So here uplift check is what, safe again, but for the sliding check there is no need to perform the sliding check because the lateral load is not there. So there will be no chances of shifting of your foundation, and when there is no lateral load, again there will be no chances of the overturning. So that's why we don't need to perform the sliding check, we don't need to perform the overturning check. In both of the cases it is what, safe and not needed to perform when your column is going to be resting at the center of your footing. Now this is what the complete design. Again, as per the problem statement, I am going to put here as 45. Once you put the 45, automatically this check will be in active mode and we are getting whether they are passing or not. So they all are safe. Now we have to look at the final schedule. So here footing number, or if suppose in group, so you have to choose the group 1, how many number of footings are there in that group. So it is a 1 footing, so you can put it as 1. And what is the length of the footing, what is the depth of the footing, these all where sheet has referred from your previous adopted values and giving the final output. And the reinforcement along the width of the footing, here it is updating. The reinforcement along the length of the footing, here it is updating. So everything is now present here. Now I have to prepare the schedule. So this is your schedule sheet. Come back. So here go to schedule. So you are in schedule sheet. You have to come back to your design sheet. Then click over this. You are coming back to your design sheet. Now I have to send this design report to my schedule sheet. So you just have to click over the send to schedule. Once you click over the send to schedule, so now this data is available in your schedule list. When you come back to design sheet, then if suppose another design you have done here, then you have to take in the group 2, and suppose number is what, 3 number of footings are there in this group, then you have to click over this send to schedule. So that is what going to be updated in your schedule list. But if you feel that last entry is done by mistake, then you can click over this clear last entry. Once you click over the clear last entry, so now in your schedule list you will find only 2 entries. So I would like to come back to design again, and if your project is completely done, then you can simply click over the clear all. Once you click over the clear all the entries from your schedule is going to be what, cleared. So guys, you don't need to go to your schedule again and again by putting it manually. With the help of this sheet, you can prepare your schedule automatically by just clicking over these buttons. And as per your design calculation as done by the spreadsheet, your detailing is also going to be updating here. Detailing for the reinforcement, so it is along the width, so width is 2 meter and depth is what, 650. And what is the length? Length of the footing is 2.3 meter, and this is the width of the footing, 2 meter. Along the width of the footing, 12 mm diameter of bar at 125. Along the length of the footing, 12 mm diameter of bar at 125. If suppose you are going to make any change, suppose along the width you are going to choose the 100 mm spacing, so accordingly here it is going to be updating along the width 12 mm diameter of bar at 100 mm center to center, along the length 12 mm diameter of bar at 125. So whatever the things you are going to choose while designing it, it is going to be updating in your detailing, and it is going to be updating in your schedule. So in respect of your design, everything is going to be prepared. Hope that you all understood how to use this spreadsheet for designing of your foundation when the foundation is going to be subjected to axial load as well as biaxial movement, and we have taken the help of this problem statement to design this foundation. Thank you all for watching this complete video till its end. If you like this video, don't forget to like, share and subscribe. And please share this video with all of your friends, those who are related to civil engineering and structural design field. Thank you.